A great pleasure to introduce Dr. Tiago Cogumbeiro, coming from University of Massachusetts, Boston. Me and Tiago know each other for a very long time. I met him when he was doing his postdoc at Imperial College. We shared passionate interest in deadlock detection and working on concurrent programs. After Imperial, Tiago moved to Rice University and believe later to Georgia Institute of Technology, and now he's assistant professor at University of Massachusetts, Boston, where he is the head of his own research group and working with several PhD students, and now he's going to speak about his latest work on verification of GPU programs.
Great.
So,
thank you so much for the kind. Yeah. Thank you for the kind introduction. Thank you for the invitation as well. Today I'm going to be talking about verifying data race freedom in GPU programs. This is joint work with Julian Lange, who is here. Also Dennis Wrong, who is my PhD student, and Hannah Ziccarelli, who is becoming my PhD student coming fall. So this is their first paper, actually, so that's very exciting for us. So today's talk, it's divided in the usual way. So we're going to talk a bit about why GPUs matter, why should you care about GPUs and GPU programming, what makes it special and difficult to analyze. And then we're going to go over how our approach of doing data race freedom analysis improves the state of the art. And finally, we're going to conclude by showing you how we actually achieve that. So first, we're going to just show you by how much we improve, and then I'm going to show you how we actually do it. So if you can zone off in any of these points and still get something out of it, hopefully. So why should you care about GPUs? Well, hopefully you've heard of them, but GPUs are just this, you can think of them as accelerators, highly parallel accelerators that were originally designed to power graphical cards, but have now been used exclusively for general purpose computation. And they are indeed everywhere. As you can see, they're basically the computing backbone of scientific advancement now. As you will see, if you look at the top 10 supercomputers, 8 out of 10 are using GPUs to power the parallelism. The two that are not using GPUs are also not American. So in the US of A, everything uses GPUs. So GPUs are are being used in chemistry and biology, and really is for a good reason. It's because it gives you an affordable way of achieving high performance parallelism. So it is actually the computing power that is under the AI revolution. For instance, if you go to this autoware.ai, which is kind of open source software for autonomous driving, you will find this is one of their various repositories. And if you go for the core perception, they're using GPUs for things like visual detection algorithms, and any kind of linear algebra is using GPUs for that. So basically all of your favorite, even TensorFlow and all that, is using GPUs on the back end, or GPU programming in the back end. So we've seen that it's prevalent, it's everywhere. So what makes GPUs or GPU programs special, that they need or they deserve any special kind of attention? Well, there are 3 main things that we want to talk about when we think about GPU programming. First of all, it's, as I mentioned before, it's a high level, you get a high level of parallelism at a reduced cost. And that's why it's interesting, right? That's why people are buying it and deciding to use it. So that gives you faster processing at a lower cost, and it also gives you reduced power consumption. So those are all good reasons to choose GPUs. The problem is, however, that the techniques people have been done and algorithms that people have designed for CPUs are not applicable for GPUs. So you really need to change your algorithm. You have to rethink your algorithm so that you can take advantage of the power given by GPUs. So because the underlying core assumptions of your hardware are completely different. So there is a reduced memory available, and the execution model is vastly different in terms of parallelism. And the summary of it in short is that GPUs are really difficult to program and debug because you don't have enough memory. So you cannot really have debuggers and these kinds of things that programmers are used to. They just don't work. So that kind of also pushes static analysis because you don't want to be able, if you don't interact with the system, that's already a good thing because its debuggability is not optimal. So when you're writing GPU programs, basically you have a high level of parallelism where you have up to tens of thousands of threads running. Not all of them are concurrent with each other. You have around 1,000, you have at most, actually it's a fixed limit, you have at most 1,024 threads accessing, that could be accessing the same array. And actually this is one of the most difficult parts of the analysis, is really that in GPU programming, as I will show you in a second, in the next few slides, people don't program concurrency or synchronization with locks or what you're used to in CPUs. But what happens is this model where all threads are accessing the same array unconstrained. So there are no locks, there's no anything. So the programmer has to be very careful to make sure that all the accesses are disjoint, otherwise you have errors. So you'll have thousands of threads indexing disjoint portions of the same array. And this is what I was saying before. Devices are memory constrained, which affects any kind of runtime technique, which is why you want to focus, or why it's desirable to look at static analysis. So just to give you an example, this is an example I took from an NVIDIA CUDA. CUDA is the most famous API to program GPUs, and NVIDIA is the most famous manufacturer. So this is from their a manual where they're explaining how to optimize matrix transpose operations. This algorithm is also extended in this paper called Padding-Free Conflict Resolution for CUDA-based matrix transpose algorithm. And we actually found a bug, a data race in this very small piece of code. And I'm going to talk a bit about it in detail, but for now, what I want you to understand first is not how to discover where the bug is. Don't try to do that unless you understand GPUs already. So for now, I just want us to focus on how would one look at this code and run it. So what is the execution model conceptually? So the idea is that when you have a GPU program, such as this one, you will find special variables. And whenever you see TID here, that's a special variable. And I highlighted them in yellow so that you can clearly see them. And the idea is that the same program that you see in this box is going to be executed in parallel by 1,000 threads, let's say. Each thread will instantiate this program and will replace this yellow box by a unique number. So each thread has a unique identifier, which we'll call the thread identifier, hence TID. And there will be an instantiation per thread. But they're all running the same code, and they're sharing the same data. So this tile that you see here, highlighted with my pointer, is being shared by all threads. So they all can write to it and read from it at the same time. And that's how they communicate. So for instance, if you could run this program, if you were to run it with just 2 threads, you could think of an identifier as in this case, the identifier is 2-dimensional. So you could have an identifier that is 0, 1, and the other one is 1, 0, and you would instantiate each box with the correct index. So you would be running the program above and concurrently with the program below, and they're both accessing the same tile array. Okay, so for now, just think of that as the execution model. So when you're running, so that's a good thing in a way, because when you're running code, you're always thinking that, you know, that it's not like one thread is going to be doing something completely different. And what is known as, you know, regular parallelism. Okay, so let's focus on, I want to define first what is a data race, this essentially the focus of this talk. So a GPU data race, or just a data race, is when two threads are accessing the same location or shared location, in this case, a shared index concurrently, and at least one of the threads is writing to it. And this is a problem because if they're doing it concurrently, it's not, the programmer cannot know whether the read and the write which one will resolve first. So what you get is a source of non-determinism, which introduces bugs. And I will show you an example of such a data race in the running example. So what data race freedom analysis does, so the focus of this talk, is to show that for all possible inputs that you may have, for all possible executions using those inputs, the program is always absent of data races. Okay, so it's difficult because you have to reason about all possible executions and all possible inputs. Okay, so a very trivial data race can occur with this program. Of course, no one would write this, but I would just want to cement the idea. So if every thread is writing to position 0, this is a trivial instance of a data race, right? Where all threads are writing to the same location, and that's considered to be an error. Okay. So imagine each thread were writing a different value, like TID, then you wouldn't even know which value would be written to this array. In this case, everyone is agreeing that is 1, but in the general case, that is considered an error. Okay, so far, so good. We know what is a data race. And now I just want to give you a very brief intuition as to why this program has a data race. And the problem, just so you know, when you're running this code, what's going to happen is you're going to unroll the upper loop, right? So essentially, you're going to run this code, and then this code is going to appear in succession. And what happens is whenever you have this idea of sync threads, that is known as a synchronization point where all threads have to wait for each other. And that is what you use to control communication, right? So if a thread writes before a sync threads, then another thread can read from the same array without this source of errors, without this source of non-determinism, because here everyone has to wait for each other, right? With the sync threads. And the data race that occurs here, we're going to see it in a bit more detail at the end of today's talk, is that the code of iteration I plus 1. So if you have iteration I, it would be this code will run concurrently with the code that follows, which is this code, right? So that means that this write will run concurrently with this read after the next iteration. And the outcome of that, so why is that bad? Well, in this case, the outer loop is a loop that is used to measure how many times a transpose operation, which is the code that you see in the body of the loop, of the outer loop, how many times you want to execute a transpose operation so that you can time it at the end. So the data race that exists does two bad things. First one, it means that when you do one transpose operation, the following will be running concurrently. So a bit of the writing of one operation will be corrupting the following reads of the next iteration. So one transpose is corrupting the data of the next one. And additionally, because one iteration is not waiting for the previous one to end, that means that you're measuring the timing. The timing gets wrong, right? So it's potentially also affecting the timing used in the optimization, right, to bring the point across. The whole objective of this exercise is to show you how to optimize the code, but the way the data race is actually affecting how you measure that optimization. Okay. So it is subtle because it is in published work, right? And no one talked about it in the published work. Okay, so now let's look at, this is just a problem. This is what we want to try to design techniques that are able to, just by looking at the source code, identify this error and say, this is where it is. This is where the error is coming from. Okay, just without running the code. So let's look at our contributions. So I'm going to divide the rest of the talk in two parts. Part one is the practical part, and part two is the theoretical part. But because I think the theoretical is more interesting, I'm going to explain it first in this slide. So the theoretical contributions that we make is we introduce a novel analysis of data race freedom. And all of the formalism, and we formalize this analysis, and we prove the correctness of our analysis using a proof assistant. The practical implications of this is that our analysis, first of all, we have an implementation of the theory, which is a good thing, right? And it's open source and you can download it and look at it. But also our approach outperforms the state of the art in many ways, which I will show you in the next slide. And this is also the largest comparative study of its kind, where we used multiple tools and ran them against each other. And it's quite difficult because of how static analysis tools in this field work. They all require this specially tailored or bespoke input, right? You always have to change the input, add a bit of code annotations to make it work. So it's really complicated if you have a large data set to make it work for all of them. You would have to change all files. And we just developed this framework to help you do that automatically. Anyways, let's show you first why our tool is better. So our tool is called Faial. And what I'm showing you in this slide is a study that we did on 227 real-world kernels. And these kernels came from various different benchmark suits and SDKs from CUDA. So from NVIDIA, sorry. So I think it's around 4 benchmark suits divided in, they're trying to optimize or show different examples of what you can do with GPU programming. And what we did was we ran our tool, GPVerify and Pug, and this is actually a data set from this tool called GPVerify. So it's already prepared input. Everything is very easy to, just run a tool against it and will doesn't have any dependencies or that kind of stuff. So that's nice. So we're using a data set that was already used in published work. And the point is that our tool can verify 40% more than the remaining, than the state of the art. So as you can see here, our tool can handle 95% of kernels, so 217. They're all correctly identified as data race free, and then there's these kernels that cannot be addressed. And they usually mean there is just like a feature that we don't handle of the API. That's usually what they mean. And GPVerify has this theoretical limitation, which is it requires you to annotate loops with a loop invariant, and that really hurts them in, if you don't have annotations, it means that their tool cannot verify a lot of the kernels. And Pug is this other tool that does not support many features. It's been abandoned for a while, unfortunately. So they only support 35% of the data set. Okay, so we have the lowest false positive rate on the data set that we used. And this is the time it took to run. So just to give you an idea, our tool is the green one here in the middle, and the green one here. And red here is Pug, and blue here, all going crazy, is GPVerify. Okay, so basically what I want you to see here is lower is better. This is a logarithmic scale. this one is linear. But essentially what I want to show you here is that our tool basically gives you a good compromise between memory and time. Right, so it doesn't explode memory or time. So Pug, for instance, is really fast, but uses a lot more memory than us. And GP-Verify is optimized to use not a lot of memory, but in terms of time, it suffers from exponential blowout very easily. Okay, so we looked at this, and then what we thought was, how can we look at the various features of code and see, kind of understand if your code only, we vary the number of ifs, or, how each control flow structure affects the analysis. That was basically our second thought experiment. So this is the results of that. What we see is if you vary the number of accesses or the number of barriers, which is that thread sync code that I showed you, or conditionals, or number of unsynchronized loops, we vary them from 1. So it's a piece of code that has 1 to 50. So on the right-hand side, you have 50. In this case, 50 accesses to the same array. And on the left-hand side, you have 1 access, right? So somewhere in the middle, you have 25. Again, on the y-axis, you have time it takes to verify the code, and on the bottom, you just have the number of instances. So what we're seeing here, ours is again green, 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 and the red is Pug, red is Pug, and blue is still GP-Verify. And what you see here is 2 more, and these 2 more, they are Gcli and Cesa, which are symbolic execution tools. These are more like dynamic analysis, or kind of a hybrid between them. You can think of them as a dynamic analysis. It's just to show that dynamic analysis is not very good. But what I want to show you here is that our tool is the only one. So here you want to have a flat and low line, right? Because if you have that, it means that your code, your analysis scales with the input. So if you grow the number of accesses, all the other tools, they grow exponentially, as you can see here. Pug doesn't even run this. So if you have a little tombstone here, it means the tool crashed. So in this case, these 3 tools, they have exponential growth, whereas we have linear growth. So in this case, if you vary the number of barriers, you will see that this tool has exponential growth, and these are all linear. And conditionals, linear, linear, and everyone has exponential except for GP-Verify. And here, number of nested loops or number of sequential loops doesn't really matter. You will see that there is a growth here, exponential, and ours is linear. And you will also notice that Cesa and Cli do not appear here, and that's because whenever you have loops and you have dynamic analysis, you don't know what's the bound, so you don't know how many times you need to run, which means the tool will time out. So this is just a characteristic of this family of tools. Okay, so this is just to show you that our tool behaves very well in terms as you grow the scale of your program. So what are the limitations? Of course, you have to have limitations, right? Where in the end, every research is about what the trade-off. And the trade-off we chose was loops that have a barrier, a synchronization, that thread sync in the code. And if you have that, we have exponential, like a very steep increase. We're still better than the dynamic tools. So we're third. So what you want to see again is lower, and you want to see it until the end. So in this case, this tool was able to process these many nested loops. So 10, 20, 30, 40. Whereas our tool is only able to handle 13 nested loops. However, what we've seen is that in the data set, in the experimental real-world kernels, the maximum level of nesting that we saw was 3. So we're within, and over there, if it's 3, we're second. So that's great. Okay, so this kind of concludes the experimental analysis. Again, if you have questions, feel free to interrupt me, or not interrupt me, just ask them away. Okay, so we're kind of halfway through the talk. And now I want to use the last 30 minutes to go through, but that includes questions, so please ask them away. Okay, assuming there are no questions, then I'll move along. So now this is our theoretical part, contributions. And what you see here is the pipeline of our analysis. But first, let me focus on the contributions. So what we propose is this a behavioral type where we give formal syntax and semantics. And that's what we use to prove the analysis, or to develop the analysis. Along with that, we also introduce results. We also prove results of correctness. So we show that these steps in green, which I will explain next, are all, they preserve data race freedom. So they are correct. So it means you can go both ways. You don't miss any data race. So any kind of when you abstract the code, any kind of I'm missing the word. Any kind of incompleteness results arise from inference. What I mean is, whenever you do some kind of, like, for instance, the way we handle loops, where we might not handle it very like go jumps or go tos in C, that would be this step. But assuming you already have a behavioral type, which is what I'll show you in today's talk, all the transformation preserves data race freedom property, the data race freedom property, which means that you don't lose any information while you go from step to step, which is interesting, I think. And all of these results were proved using a proof assistant called Cog, and it's quite a big. It's actually the biggest project I've done so far. It's 18,000 lines of code. A lot of it is because of the way, you have a language per level, so you kind of have to do a lot of proofs over and over again. I couldn't find a better way to do this, so that's kind of like what we have. Okay, so now let me go through a simplified example. So this is a simplification of the running example, just so I can have a more reasonable. Oh, I do have, actually, let me explain the pipeline first before I go into that. So in the pipeline, what we have is we have an original program, and I want to show it to you. I'm still sharing the screen. I want to give a short demo as well. So you have a CUDA program, which is your C source program. And then what we do is we infer an abstraction of it, which we call behavioral type that we call memory access protocols. So it's that S right here. And then we have a series of steps that it kind of works like a compiler. So we kind of transform that protocol or that program abstraction over and over until we reach to this point where we're generating an SMT formula, which we send to a SMT solver, which in this case we use Z3. And basically, if the solver can solve something, it means it found a data race. So it found a combination or a combination of state variables, so the variables of your program. So if you assign values to it, you will be able to reproduce the data race. And I'll show you an example in a moment. So this is more or less what happens. It goes from step to step, where we first take just the well-formedness. It's just like a sanity check, if you will. But here there's an important thing that I will show, which is we distinguish between synchronized and unsynchronized loops. And then we do two steps called aligning and splitting. And eventually quantification is what I'll show at the end. Finally, we generate the SMT formula, as I mentioned. So let's look at this running example where we kind of simplify the original, that example I showed you with all of these loops. A few simplifications I did was my thread IDs are now one-dimensional, as is my array. Before it was a two-dimensional array, now it's one-dimensional. And that is really for the sake of presentation. You don't want to have, I can show you what happens when you have a two-dimensional array in a second. So this is our C program, and I hope you believe me that this is very close to what we had before. I also elided the code that it wasn't useful, but what I want you to focus on is that there is a write to this tile array, and there's a read from this tile array, right? And sync threads is, again, the way where that synchronization point where all threads wait for each other. What is important here is that this program races for the same root cause, which we'll cover in a moment. Okay. So what we do. So the way our pipeline works is we take the CUDA program and we abstract it away. So what you see here is kind of, if you squint your eyes, you will see that there's a 4, and the 4s are basically the same. We just renamed sync threads to sync, so it's kind of shorter. It's not super important. And now we have, basically, we're going to have one of these abstractions per array, right? So if you have 3 arrays, you're going to have 3 of these. Okay. And then what we're going to do is just some syntactic transformation to simplify the analysis, which also makes the analysis compositional, so faster. So from 2 to 3, that's called barrier aligning. And finally, what we're going to do is the step known as barrier splitting is where we show that you can actually analyze the code between 2 sinks independently from one another, because it's impossible to have a data race from here to here, from here to here. Although in the non-aligned version, it is possible to have a data race between this code and this code, as I just showed you. But in the aligned version, it is not, so the analysis is much simpler. That's kind of like the contribution of our work, or one of the major contributions of our work. Of course, showing that that works is the crux. And finally, each of these fragments can be proved independently, and the proof is going to be something like this, which is essentially a flattening. So this block of code actually corresponds to this code here. So you'll see we kind of look at each for loop as have a way to interpret as a for all binder, and we'll see that in the end. Okay. Any questions so far? Okay, so just to show you that we do what we preach. So first, I hope everyone can read this example. So this is the example I'm showing you right here. There's a bit more code before, kind of to initialize indexes, but this is exactly the code I showed you in the slides, right? Which is this code right here. So what we do is first step is inference, right? So it's where we understand the code, or our understanding, or our tool's understanding of the code, which is this step right here. And then there's some alignment, which is the next step, where we kind of rewrite the code, and this version should match this version. As you can see, no, wait, it's the next one, sorry. Okay, now it matches. So you can see that there's a for each, which is this for each, and then there's this big loop, which is this big loop, and then this small loop right here, which is going to be this small loop right here. Okay. Of course, the real version, that's why I don't want to show you the real version. There's lots of noise. And then eventually you get to a point where you can split it into multiple things. So each of these is what I was trying to show you in this block, where you have one block for each thing between sinks. Okay, it's more or less the idea. And then the final output is, the final output is all of this code. This is 3 SMT formulas. As you can see, they can become quite verbose. Okay. So in the paper, we actually explain how to generate the SMT formula in a way more concise way. So I think it's digestible there. Okay, so let's talk a bit about the 3 major things. So a bit about inference, a bit about barrier aligning, and finally a bit about splitting in the last minutes that I have. So the first one, inference, as I showed you, is just a way to we define this behavioral type that is capturing control flow, right? Because that influences the kind of errors that we're interested in. We also have to capture synchronization. And finally, we have to capture communication, which is the reads and the writes. And that is typical of behavioral types. So what we have first process is inference, right? Where we take a program and we infer its type. Or if you don't speak types, this is just a program abstraction where you get some kind of intermediate representation, right? But the importance here is that by making the this intermediate representation first class, you can build a theory on it, and you can do a lot of tools and simplifications on this intermediate representation. Kind of like if you think about it, LLVM, where everyone is generating the same thing, and you can develop all these tools on the same like intermediate representation. One very important thing of our language is that it distinguishes between synchronized and unsynchronized loops. And this is it's trivially done because you only have to, there's a little s if there's a sync inside of its body, and there's a little u if there's no sync inside of its body. So it's pretty obvious. We just annotate the loops, okay? Nothing too complicated. And of course, we only represent code essentially that is affecting the indices that are used in the arrays. So that's part of the inference process. So we also only support structured loops. So as part of the inference process is really to either infer loops and all that stuff. You know, because in C you can have while loops, and you may be able to convert them to structured loops and so on. So when I say structured loops, I mean loops where you know the lower bound and upper bound and the step. Okay, so this is more or less what we have. So this is what we have in terms of inference, and this is our behavioral type. So in order for me to explain finally get to the point where I can explain where the data race comes from, I think protocols make a really good argument for that, because they clean up all the code that is unrelated. So we don't want to talk about anything else. We don't, you know, if you look at the actual code, actually, let me show you let me pull up the actual code. Diagonal transpose. You know, has all this ifs here, all this initialization. All of this is really not super necessary to understand. What you really want to understand is, you know, for each array, because data arrays are per array. So you just want to look at, okay, for this array, what are the reads and the writes and the code that affects it. So we can reason about the data arrays very easily. So what I'm going to do now is, if you think this is as I showed before, this is the type of this program, right? So it represents that program. And what I want to do now is, if you think about it, it's execution, right? Where you unfold this loop once, the outer loop. What you will have is, you will have in the first iteration, you will have this code followed by this code, right? So you will have something like this, right? Where this code is R0, an iteration R0, and then in iteration R1, you'll run this code. And then you'll have a sync afterwards, right? And before this, you would have this a sync and then this loop, right? But it doesn't matter. What we want to focus is the interaction between this code and what follows, right? So we can write a protocol for that. So that's what we do. And in this protocol, there's no sync because it's only the unsynchronized fragment that we're interested in. So hence the U here. So we have first what appears first, which is this read, and then what follows, the write. So now what I want to do is I want to show you how you can spot the data race here, okay, if you haven't already. So the big idea that we show in our paper with respect to this part of the analysis is that we can look at these for loops and we can interpret them as for all binders without loss of generality. And this is important because what that means intuitively is that you can look at this code, right? And the first thing I told you to show how the execution model works is, well, I could have two versions of this code, right? One for one thread, another one for another thread. The objective of the proof is to figure out if there's any concurrent reads and writes. So is there a read and a write, or a write and a write? They're accessing the same location, but they're different threads. That's our objective, right? So what we could do, we can instantiate this code for 2 if you want to think about what is the version of 1 and the version of the other thread. And if you abstract away what thread identifier you're using, you can reason about all possible threads, right? So you can think about 2 copies of this program, how they would interact concurrently, right? So then what we can do is we can reinterpret each for as for all binders, which is what we do in the bottom. So these 2 for loops can be seen as the union of all the one read of an arbitrary iteration and one write of another arbitrary iteration, running concurrently with just a single iteration of this read and a single iteration of this write. Okay. So just to clarify, and I'm going to emphasize this again, we're not unrolling the loop. These 2 loops, when we're reasoning about it, we're just reasoning about a single iteration, not the whole loop unrolled. And that's why, so you are analyzing just a single iteration. What you do have is a for all that ranges over all possible combination of these. But for an SMT solver, it does matter, you know, whether you have, because that's the difference between generating, you know, if you have a loop with 1,000 instructions, 1,000 iterations, you would have 1,000 steps unrolled versus just having 2. Right. So in this case, we kind of fix how many instances we need to prove the result. So what we're saying is we only need 1 instruction per loop. And that's what we have here. And then the objective is, do these 2 things race? And then what the solver will tell us is, yes, it will race when this is 0 and this is 1. So you would have a read on 1. And then here, when this is 1. So if this T2 is 1, then this is writing to 1 and the other one is reading to 1. So therefore you would have a data race. Okay, so this is much simpler than looking at the original code and trying to figure out where the data race exists. Hopefully. Right? Also, you have a more localized. So ideally what we would like is just to have these fragments of unsynchronized code where we would reason about them. Right? That's what we would like. But that's not what we have. Right? What we have is code like this that has a sink in the middle. So what we show is that there is always a way where you take a program that is what we called here misaligned, and we kind of massage it and transform the code so that it becomes aligned. Okay? And the key point here to remember is that this idea of leakage, right? And what happens here, when this code runs, the access here, they're leaking, and they may run concurrently with the accesses that appear in the beginning of the iteration. So ideally, what we would like to have is a sink at the end of the iteration, either at the end or at the beginning. But you will see that at the end is nicer, actually. So that's why we do it here. And then what we do is just we reorganize the code, and this has to be done recursively. And that's why we have that exponential blowout, because the algorithm is recursive, and it's kind of, you take something that is aligned and then you kind of spill it around. And the intuition behind this transformation is really you unroll the loop 1 iteration, and then you reorganize the body so that it terminates with the sink here. And it's always possible. And it preserves actually all, if you go from here to here, this is exactly equivalent program. So you'll have all the same accesses in here that are in here. So you don't lose any information through this transformation, okay? And this we proved. We proved that. So the next step that I want to talk about, or the last step that I want to talk about, is once you have this really nice syntax-oriented transformation, once we have this aligned program, we now can do a syntax-oriented transformation, right? Which is to say, whenever you find a sink, take all of that, and that is an unsynchronized piece of code, right? And you can analyze this independently. So what do we do when we have a synchronized for loop? Okay, so we have to extend the analysis, right? When we have a synchronized for loop, what's going to happen is that every thread is going to start this loop together at the same time, right? So they're all going to see R to take the value of 1. And then they all synchronized, right? They all have to wait for each other. And then they all run, and they will all see R to be 2. So it's always it's always the case where every thread observes the same value. So R is going to be observed by all threads equally. So they all are going to see the same value whenever you have a synchronized loop, and hence why you need the modifier here, or the annotation. Okay, so the point now is when you can interpret a synchronized for loop with a for all binder, as long as you ensure that you use a single binder for both threads. And that's what we're doing here. So again, we kind of took the previous code, which had this expression, and we just added a new condition, which is to say that R exists, and it's constrained between 1 and n. Hence this thing in green. And that's the basic idea of Berry splitting. And this is very important because it tells us not only can you do a syntactic-oriented extraction of unsynchronized fragments, but it also means that your analysis can be done in parallel, embarrassingly in parallel, right? You can analyze each fragment independently of the other. And we also saw how we can reinterpret or interpret synchronized loop variables as for all binders. And it has to have a special treatment that is distinct from unsynchronized loops. And finally, yeah, we saw also this, that the binder has to be shared by both threads. Okay. Okay, and that's basically it, what I wanted to talk about. So in summary, I showed you how to use behavioral types or a use of behavioral types to analyze data race freedom, or how to use these types to enforce data race freedom. That's another way of looking at it. I showed you a compositional analysis that is formally proved. We did a large experimental evaluation with around almost 500 kernels, half of which are real world, half of which are syntactic experiments. I didn't show you a few more. In the paper, we do a deep analysis of a smaller number of kernels, like 8 kernels, I think. And that's interesting because it kind of shows the precision of our tool. And that's a more in-depth analysis of related work. So we use our tool to configure data races found in a while. So I showed you that initial example that is found in two algorithms that are in published work. And I showed you that our approach is more scalable and more precise than related work. The source code and proofs are all available in a free software license, and I'm very excited about looking at possible collaborations and uses of our tool. So this is the tool, Faial, and Faial Coq is the formalism, the proofs. Okay, and that concludes my talk. Thank you, everyone.
So thank you very much, Tiago, for the very exciting talk. So now we will be taking questions. So if you have questions, please raise your hand, or actually I think you all have the permission to talk, so you can maybe directly talk or ask on the chat. Let's see if we have any questions from the audience, and if not, I have several questions on my own that I'll interrogate you. Okay, yes, we have a question. So yeah, I'll test it.
Okay, yeah, so it looks very cool work and great talk, very nice.
Thank you.
And I have maybe a naive question because I'm not an expert in GPUs, but I was wondering whether, I guess, your approach can also be adapted to OpenCL if you want to analyze the same issues on OpenCL. There are not many differences, I guess, between CUDA.
Correct.
That are relevant for you. Oh, okay.
Same programming model. Yeah. In fact, it's not that difficult even. It's just like GPVerify, for instance, they apply their technique to both OpenCL and GP and CUDA, exactly because of that. The programming model is the same, it just has different names. So for us, thinking about in terms of types, there's no change. Yeah.
Yes, thanks.
It's just a matter of engineering. Thank you for your question.
And talking about engineering, so how hard was to infer the types from the CUDA programs? And you mentioned that you have these few features that you're not supporting, and you say that, well, that's just because of inference. So can you mention it, or do you see anything that you really struggle to extend the tool with?
Thanks for the question. Yeah, inference is kind of it was easier than I anticipated. You know, in the beginning, I had never done a work where I would analyze C, so that seemed really really crazy in the beginning. But once you start working on it, actually GPU programs are very well behaved for the most part, because of what you can do, which is not a lot. And that kind of gives you a big benefit. It means that there's not a lot of features to cover. A lot of so the first stage of the research was really going through large data sets and looking at what do people usually do. Usually people have structured loops. So just starting with those concessions really made our research advance quite fast. So in terms of development time, I'm not really sure. I know that we still struggle with things like, for instance, if you look at the example, let me share the screen real quick. Okay, so if you look at, this is the original example, and you see this if here, where you have equals assignments in if and ifs. That usually is a problem for our analysis. We do accept it if it's the ternary operator, but whenever you have these kinds of ifs with assignments, that is complicated because in our analysis, we don't do very well with this kind of things. And whenever you have a loop and you have incrementing a counter, for instance, that really can throw off our analysis. But that's like classic compilers, and we just didn't have time. It means that we need a better SSA representation and algorithm. But the major difficulties that we found, like to be able to get those 95% of the data set, it was really a lot of small things. It wasn't like really big things didn't affect, like not supporting indexes being updated in loops. No code has that, at least in the data set that we looked at. So it was like supporting really small things, a lot of really small things that spent a lot of time, but that made us support the code like 90%, 95% of the code.
Yeah, I see. So we have another question from Fanny.
Hi, thanks for the talk. So basically my question is, well, partially covered by you just now, which is how do you deal with conditionals? And well, I was picturing a scenario where there's an if and if with some condition and some assignments are done on the then side and some assignments on the else side, eventually you do a synchronization. How do you deal with that thing?
Yeah, so that can be, if you use an SSA representation, you can actually inline the assignments so that you don't have, you have a single assignment, you can go through it, and that would kind of obviate this problem. We fully support conditionals, by the way. So if you have ifs in our code, let me kind of see if I have another example. But we do support ifs of course, in our formalism and in our tool, because if you have conditionals and then you have synchronization, that's fine. What we have more limited support is conditionals with barriers in the middle, where the body has a synchronization, and that's for a good reason. It's actually CUDA disallows, you cannot have code that has a conditional and you have some thread local variables in the condition, because that would mean that some barriers would synchronize and some would not, and that's outside of the spec. So you cannot have that code, which is good for us. But we do fully support conditionals, by the way. It's just if your counters are in conditionals and are being mutated, that can present a problem, but it can be easily solved by a better SSA analysis. Single static assignment analysis.
Yeah, may I just ask a quick follow-up? So what if they cannot be modeled as ternaries, for example, if they access a different set of memory locations in the conditional?
So if accessing different arrays does not pose a problem for data races, if that's your question.
They're accessing the same array but different indices, so they would produce a different read and write set.
That's completely fine. You can have if and then accesses in one branch and then else completely different accesses in another branch, and that's fine. That happens a lot. That's very common.
All right, thank you.
Yeah. If you want, after with more time, I can show you examples where you have like loops with where you want to do reduction, for instance, a very common pattern in GPU programming. And what you do is you kind of divide your threads into pairs. So you do first 1/2 and then you divide by 2. You have 1,000, 512, 256, and so on. So for that, you need to have conditional accesses on the arrays. And that is fully supported by our analysis.